As said, I'm Michelle Simoneau. I am one of the program chairs and moderators for this presentation. I am with Stantec Consulting, and I'm just going to give you kind of the flavor and flow of what to expect by giving you just a brief introduction to the program. So as you know, whether we're undertaking a dredging project for navigational purposes, for a water-dependent structure or facility, or for an environmental remediation project, one of the biggest challenges that we face is when we're designing and permitting and implementing the project is what to do with the sediment, and trying to find an economically and environmentally sound and feasible option for disposing of that sediment. An even bigger challenge to this question is when the material is comprised of highly contaminated sediments known as unacceptably contaminated sediments, or UCSs. We're so pleased today to come together to learn about one of the solutions to what to do with this type of material, and that is to place it in a confined aquatic disposal cell, also known as a CAD cell. Through our program today, we'll learn about the history, design, permitting, and use of CAD cells in New England. There are quite a few CAD cells already in use all along the coastline of New England, and they're serving as a cost-effective disposal site for projects with highly contaminated sediment. Drawing on the knowledge and experience of experts in the field, including government officials, engineers, environmental consultants, and marine dredging contractors, we'll learn things like exactly what is a CAD cell, what design considerations are taken into account, siting selection and assessment for CAD cells, and construction, and what permissions and authorizations are needed to establish a CAD cell. And then, of course, from the marine dredging contractor, kind of the realities of implementing or establishing a CAD cell, which is often designed by others. So the flow of the program, sorry, I have cat chaos here. The flow of the program is intended to lead us through the process to kind of build on our knowledge as we go, starting with Steve Wolf from the US EPA, discussing the evolution of CAD cell design and use in New England, and then having Dr. Ram Mohan discuss talking with us about CAD cell planning, design, and construction considerations. Next up, we'll have Bill Hansen from the Great Lakes Dredge and Dock Company, who provide a great dredging contractor's perspective on CAD cells, some of the challenges faced in implementing these projects that are designed and permitted by others, and lessons learned on some of the projects that he has personally undertaken. Then, to wrap up today's formal speaking presentation and bring together a lot of the great information that we will hear from the other exceptional speakers, we'll hear from Michael Johnson of Stantec, who will focus on the Portland Harbor CAD cell project that he's been involved with for approximately 5 years, and kind of dive into the project case history of the only CAD cell that's been permitted in the state of Maine. Then you hopefully will be able to stick around. As Payson mentioned, we're going to have kind of a round table with the speakers who were kind enough to stick around after the presentation. That will be at 10:55. Now I'm just going to introduce each speaker in turn, but I'll encourage you to go to the program agenda and just check it out. Each speaker has a great bio summary that kind of demonstrates or discusses their professional experience a little bit further. So now for our first presentation, I'd like to introduce Steve Wolf, who is the Regional Regional Dredging Coordinator, try that again, of the U.S. Environmental Protection Agency Region 1, which is here in New England. He is going to speak on the evolution of CAD cell design and use in New England. With that, I'll turn it over to Steve.
Great, thank you, Michelle. Let me pull up my screen here. Yes, as Payson and Michelle said, I'm actually at EPA now, but historically, I've only been here about a year, and spent the 10 years before that at the Corps of Engineers, and then a long time before that doing environmental consulting. And pretty much the majority of my career in all three of these different hats that I've worn have involved CAD cells in some form or fashion. So I've really seen the evolution of them as we've kind of come up through it. And so I'm happy. It's actually really, I find it enjoyable to kind of go back through the history here and do some presenting. First off, I'll talk a little bit about what we're not covering today. There are some terms that often get confused with CAD cells. CDFs are confined disposal facilities, where either an area of a shoreline or a separate island, as you see in the upper photo there, is bermed off, and the sediment, could be contaminated sediment, is placed inside of it. And then what we call level bottom capping in the bottom figures, where material, unsuitable contaminated material, is placed on an open seabed and then sequentially covered with layers of clean capping material. That has happened a good bit historically. It's less frequent now, but neither of those are the topic for today. We're focusing on constructed confined aquatic disposal cell. And I'll just walk you through sort of the quick steps here. In the next talk, Ram will give you a lot of details about what you have to do specifically to plan for and design these. But so it breaks down to 5 easy steps. You know, typically the cells are going to be in an area where, in a harbor, where you've got some superficial contamination, so that superficial material has to be scraped off, and you have to store it somewhere while you're actually creating your cell. Then you remove the underlying native material, which hopefully is of the quality and the type that you can find a beneficial use for. That's often been the case. If not, it should be suitable for open water disposal. Then your disposal into the CAD cells, typically through split-hulled scows, as the one you showed here. We typically don't have the lines drawn on the water, but it's pretty easy to position them. Then once the cell is filled, you've got a consolidation period to let that material settle in the cell, and then capping if it's required. And I know folks will talk more about that as I will as well. So that's it in a nutshell. Actually, CAD cells here in New England go back 40 years. Norwalk, first cell, there are 2 cells which were constructed in 1981. New Bedford, a couple of cells, they're a little over 30 years ago. But both of those I would call as really pilot or research projects. They were small scale, really with an end of trying to deal with some contaminated material and see sort of how this technique would work. And really the first major use actually in the country was the set of cells which were constructed in Boston Harbor, designed in the early 1990s and then constructed in the late 90s. And that the first round of those included 9 cells. And then based on that, a series of other harbors kind of sprung off of it. Hyannis in 98, Providence in 2003, New London, the Navy, a couple of cells in 2006, and then additional cells back in New Bedford Harbor. But it was really Boston which kicked it off at sort of the first major use. And like a lot of harbors in New England, and I think around the country, that hadn't been dredged really since the implementation of environmental regulations. Once they realized their sediments were contaminated and they couldn't take them offshore, classic sort of harbor sediments, such as what you see in the photo here, that tested, again, elevated both organics and inorganics. Maybe you're starting to see a little bit of toxicity show up in some of the biological testing. They were really at a quandary as to what to do with them. And so then building on some of that knowledge from the pilot cells, as well as what was happening in some other parts of the country, but also over in Europe, CAD cells came on the radar as probably one of the lowest risks, most cost-effective alternatives. But given that this was really the first major use of CAD cells in a navigation project, there was a lot of concern, a lot of monitoring and oversight was required of it. And fortunately, the company that I worked for was selected to basically operate in an observer role. CZM provides some funds to pull together, organize a technical advisory committee, a fairly broad committee. And then as an observer, I had a role of basically overseeing a lot of the monitoring and reporting back to this committee. And again, a lot of decisions were made if data was evaluated in real time that allowed the project to move forward. And I think a lot of the information that was gained to be disseminated out of it. So onto the actual design, the core designers had originally conceived of probably more than 40 cells, kind of a cookie cutter approach, as you see in the figure in the upper right. Shallow cells kind of spread all along the upper reaches of the harbor, the Mystic, the Chelsea, the inner confluence. But fortunately, when they put it out to bid, they basically left the actual design open-ended and just said, you know, this is the objectives of what we want to accomplish here. And then folks like Great Lakes, and you'll hear from Bill here in his talk shortly, basically took that and said, well, how can we improve on sort of this basic level of design? And really came up with a much more cost-effective approach, which included far fewer cells, but a lot larger and deeper cells. And you can kind of see them in the bathymetric traces shown here, the majority of them up in the Mystic River. So again, a lot of initial concerns, a lot of lessons learned out of this, and I'll kind of tick through what came out of Boston. First off was the residuals during construction. As I said, you know, you have to scrape off the contaminated material at the surface before you construct the cell and give some sort of a layback around the edges. But anybody who's done any kind of remedial dredges knows that you're going to have some residuals. And so that needed to be addressed with the agencies, that at least on a visual level, there was going to be some residuals showing up in the native material as the construction of the cell started. But from an overall mass standpoint, it was minor. And so we were able to move beyond that concern. Then there were a lot of concerns about opening up a scow in a harbor and letting several thousand cubic yards of fairly contaminated material, you know, drop out into the fairly shallow harbor. And for this one, a lot of work had been done at MIT, both numerical modeling as well as some physical models that really demonstrated, given the hydrodynamics of the system, the scow sits so close to the lip of the cell that really the material, even though it's fairly fluid, ended up, you know, creating a density plume which went directly into the cell. And there really isn't a lot of release to the water column. It really doesn't feel the overflowing currents that are operating in the harbor. So that ended up, again, with a lot of fanfare, a lot of concern, not being a specific issue related to the project. Then there were concerns about the sizes of the cell and tracking the capacity. Again, given that this material is so fluid as it goes in, it's maintenance material, it bulks up some because an environmental bucket is being used to dredge it. And then it's tripped through the water column into the cell, that oftentimes, especially if there were multiple disposal events happening over the course of a particular day, you really couldn't see into the cell with bathymetry, traditional bathymetry. It was hard to see sort of where the level was. And so that's where Great Lakes, I think, took to advantage having multiple cells and kind of playing one off the other in terms of allowing this material to settle. There really was only one instance, one of the smaller starter cells, where it appeared that as it was nearing capacity, some material that was released created maybe an internal wave which splashed out essentially over the sides of the cell and had to be cleaned up. But that was really the only sort of issue associated with the disposal itself. There were a lot of concerns given that these cells were in an active harbor and some very large vessels. You can see the LNG tanker, which is directly over one of the cells in the Mystic River here, being a concern, not so much of the prop wash as it was just the displacement of these vessels as they go over it, even at slow speeds. And so some considerations were given in terms of the timing, allowing the material at least several hours to consolidate, to settle before planned traffic was going to come into the harbor. Because this project went on for several years, there were concerns about the depressions that they left on the harbor bottom that could potentially be depressed, dissolved oxygen areas. So some monitoring was done associated with that. But again, given sort of the passage of vessels, the normal flushing of the harbor, DO excursions really didn't seem to be an issue there. And probably one of the biggest sort of monitoring pieces and learning curves was the capping. Again, because this was a sort of a new concept, there was an interest in capping those on the state's part as soon as possible. And the state required the use of sand basically for the capping. such that one, you could discern the cap layer very easily physically, as well as the potential for creating a sort of a new habitat type in the harbor, which was traditionally fine grained. What you can see in the upper photo here, Great Lakes, again, another innovation, dredged sand from the Cape Cod Canal, brought it up in their hopper, teed up a tugboat on the side of it and pushed it sideways. Really, that was an excellent approach for evenly spreading the sand across the cell. But as I said, there was a learning curve here. It took basically 4 rounds. The first, the time of consolidation for the first couple of cells was as short as a few weeks. To the last set of cells was, I think, approaching a year or 9 months. And it really took that long for the material in the cells to consolidate enough such that it would hold the sand layer up on the top of it. And then there was a lot of interest in looking at the performance of these cells after the fact. In the upper shot, you can see some video images to look at the benthic recovery, some images from sediment profile camera in the lower left. In the upper right, there were tracers, fluorescent tracers, which were released. In the end, it was pretty much as your intuition would say. These cells, by design, are going to end up depressed below the harbor bottom. You're always going to give them some additional capacity. They're always going to consolidate over time. And they basically ended up being a trap. And so it became clear that it wasn't maybe necessary to cap these, maybe particularly with a separate sand material, because they're essentially self-capping on their own. Maybe they could be charged with some suitable maintenance material from somewhere else in the harbor. And so that was a clear lesson learned. If we drop back to say, sort of, what did we take away from this overall Boston Harbor project? If we look at sediment contamination as being a gradient, where on the right, you've got clean, suitable material, which could be beneficially used. And on the left, we've got very high contamination levels, maybe some separate phase product. Boston fell somewhere in the middle here, maybe a little closer to the contaminated side, because we began to see some toxicity in some of that sediment. But by and large, it was very much of a success. This material was sequestered, required very little transportation and handling, so the overall risk associated was fairly low. So then, building on that, the Corps moved on to Providence Harbor. Following the same construction model, a couple of changes happened here. The state retained an entire cell for their own use for both state peers as well as some private entities, charged a tipping fee for material to go in. And they didn't require a sand cap or short-term capping. They left them open, put in as much material as they actually could. And because there are greater currents in Providence, there was a little bit more focus on water column monitoring. And what you see here on the right panel are a series of acoustic Doppler profiles, some really good information that compared predictive modeling against water column, that we see that any disturbance into the water column from a release of the sediment was really fairly short-lived and didn't proceed very far from the cell itself. And a lot of this stuff got documented, a lot of presentations and conferences. There's a lot on the Corps' Deimos website, which I give a link here, a number of publications. There were 2 standalone reports for the Boston Harbor with a lot of the lessons learned in there. Again, the idea was that the Corps and I think Massport in particular saw the states the benefit of getting the word out there. And that word was taken to New Bedford, where if we look at our sediment contamination gradient, we've actually slid the arrow further over to the left here, more contaminated material, where not only some sort of state enhanced remedy material, but also some Superfund material, higher levels of PCBs, was actually placed into CAD cells very successfully with a tremendous cost savings to the remediation of the harbor. Again, this was, that it's more contaminated material. There was additional focus on the dredging itself, using more of a remedial approach for the dredging, and more controls placed on the disposal, where now it wasn't a free large scow, but actually a smaller scow where the CAD cell was encircled by silk curtains, but actually ended up being very much of a success. So with that, I would close and say, we've had a lot of successes here in New England. And I think building on that, we've got 3 ports here that are sort of in the progress of it. Probably the furthest along is Portland, which Michael will be talking about sort of in a later talk here. New Haven is probably next, and then Beverly is really in just the conceptual stage right now. But with the note that, these are not considered, this is really considered an interim solution. We're oftentimes dealing with sediments that were laid down many decades ago and really have just been sitting in place waiting for us to come up with a solution as to what to do with them. But given all of the advances that we have in putting controls on watersheds and release of contaminated material, the goal is that we really shouldn't have to deal with contaminated sediments so much once we get rid of most of these legacy sediments in our harbors. And I think with that, I should be in good shape here. And I'm happy to take any questions.
Thanks, Steve. I don't see any in the chat at the moment, so feel free to either unmute yourself and ask Steve directly. We have a couple of minutes here for questions, and we can save more to the end. But Steve, you said the New Bedford cell has kind of moved the sediment contamination a little bit farther down that gradient that you mentioned. Do you see a limit for that with CAD cells of how far it can go, extend down that to additional Superfund sediments from Superfund sites or other highly contaminated cells or sediment?
Yeah, I think you could probably get a few more notches over from New Bedford. Clearly, you're not going to put separate phase product in, especially if you've got a release of a sheen or something to a water column. And it really comes down to the water column release, the trip through the water column. How well can you contain that? One of the things, and Bill may touch on this in his talk, is that the deeper that the cells are, essentially, the more contained the material is at the bottom. And this happens somewhat by default in Boston, but I think as sort of by design in both New Bedford and in Providence, which was you create your cell and you put your worst material on the bottom, and then you kind of work your way up. And essentially that material is sequestered right from the get-go by the next sort of layer that's placed on top of it. The other consideration, and I believe this was done some in New Bedford, which is you could charge while maybe your cell may be open for an extended period of time. Well, you put in a couple of charging layers within that, some coarser grain material that maybe has some activated carbon in it to begin the consolidation process, but the activated carbon to begin to absorb what might be discharged from the pore water, which is being expressed as the consolidation moves forward.
Thanks. Yeah, thanks. That's very interesting. And does any other questions? Last call for questions until we let Steve go and get some coffee and come back for the panel. Keith, I see your hand waving. Can you want to unmute yourself?
Yep, thank you. The who are the lead agencies in permitting something like this? It seems that there has to be a substantial role by the state to work with the Corps and whoever all the environmental agencies are. Who takes the lead in something like this?
That's a really good question. And I think Michael will address some of that related to the Portland cell, which is very much a little bit of a different model. The Corps hasn't taken the lead on that. That's a city one. But I would say in each one of these, there's been a little bit different model. Typically, for the larger ones, it's the Corps taking the lead because it's a federal navigation project, but they require a local sponsor, typically a port authority, which then that has been worked out ahead of time that says, the Port Authority for an additional share would like to have some remaining capacity in the cells. And so that's, again, something that requires some foresight, both at the state level and at the Corps level. And I think for Boston, again, sort of laid the groundwork for a model that worked well. we're starting to see the evolution of that down in Connecticut at this point, where now it requires typically some level of funding on a state part to basically prime the pump there. And so it requires, I think, some push from the local level, from private applicants who may want to use a CAD cell through their congressional reps to then begin to free up some of at least the investigation funds, either on a state level or through a core sponsorship to begin to do that. But in the end, I think there are multiple models here. You'll hear a little bit of a different one from Michael, and it's probably a good thing for us to discuss in the panel, which is, are there ways to make this easier? Because Beverly, I think, is at the point, Beverly Harbor, which is stymied with some, again, older, very contaminated material, trying to figure out how they do that on their own when there isn't a federal navigation channel, which is basically going to take the lead on it.
Thanks.
Thanks, Keith. Bill, do you have a quick question for Steve? And then
Yeah, I do. If fellow panelists are allowed to ask questions. So I think one of the interesting things that you brought up, Steve, and maybe we could talk about this more in future discussions, but the dredge material disposal area capacity is a problem around the country, whether it's in water or upland. And the concept of having the feds take the lead on these projects it's fine, but there is a lot of non-federal dredging that takes place in every harbor, and that material needs a place to go as well. And many times it can be quite contentious to work out the details of tipping fees and who pays for what and all that. So I think some success stories, if there as there are any, would be welcome to be heard around the country. So appreciate you bringing that up.
Yep, and that's a really good point, because there's quite a step function. And if you look at cost per cubic yard of a traditional dredging project, a large one, and then if you say I've got to go upland, it's a huge step. And the CAD cell certainly is more expensive per yard, but it's not that of an unreasonable step. And I think, there are a lot of private applicants who basically can't, they just basically can't dredge if they're forced to go upland. And so this becomes a reasonable alternative, but they can't do all of the background work, the capital needed to basically create the thing in the first place.
Thanks, Steve and Bill. Michelle, you want to introduce the next speaker?
Sure. Thank you so much, Steve. That was a great presentation. And thank you for kicking off the program with such a great umbrella of topics. So our next speaker is Dr. Ram Mohan. He is a principal with Anchor QEA, as well as an adjunct professor and director of the Center for Dredging Studies at Texas A&M, and also a member of the National Academy of Sciences Marine Board. He is going to be speaking on the review of CAD cell planning, design, and construction considerations based on past case studies. You're up, Dr. Ram.
Thank you, Michelle, and good morning, everyone. Thank you. So Steve gave a very fascinating discussion on the New England CAD cells, and I will pick up on that, maybe focus on a few key considerations during design, and then look at a few case studies in areas outside of New England to give you a bit of a national perspective. And then I'm sure Bill will come and wrap it up nicely with more of the construction-oriented discussion. So essentially, this is our tools in the toolbox, which you see here. So on the very left-hand side, we have the upland containment options, whether that's in an in situ depression kind of area, or building a traditional CDF, confined disposal facility, or doing a nearshore CDF. And then we go into the realm of what we call CAD cell for the purpose of discussion today, to more confined placement facilities in the ocean itself or in the harbors and bays. So that's really the suite of options we have, and each has its own intricacies in terms of the design considerations, what type of material you put in there. Obviously to the left, it's more contaminated. This is, I would call, mild to clean to mild to moderate contamination. These are again higher contamination. Then you have, of course, open ocean placement on the very right side of the spectrum here. But at a high level, what is a CAD cell? So Steve touched upon this. A CAD cell is essentially, a system that provides isolation, and the degree of isolation really depends on the type of material we put in there. So if it is clean sediments, we probably don't need to put a cap there. If it's contaminated, we'd almost definitely have to put a cap there. And then I'll talk a little bit later about other considerations. But when you look at our journey through this, New England certainly is at the forefront, and the program Steve used to lead, the DAMOS Disposal Area Monitoring System, was the program that I actually started my career with when I was at URI in grad school, looking at sites at Sandhaven and Connecticut shorelines, looking at level bottom CAD and the efficiency of capping, all of which we have taken those science and now applied to these cell concept. The cell concept was also talked about in New York. I mean, there was, they called it a sub-channel placement in the early 90s or late 90s, I should say. I don't think that went many places, but the concept there was a modification of what we in the dredging industry used to call advanced maintenance dredging. So instead of dredging deeper, this was you dredge way deeper and provide this facility where you can move sediments into. Interesting concept, not sure why it didn't take off the ground. In the Northwest, in Washington primarily, there's been a lot of CAD cells. California is very closely following, LA, Long Beach, those areas. I have a couple case studies there. Maryland is embarking, testing that concept. And then we, of course, have a few of those in the Gulf Coast. So in terms of siting considerations, obviously the cardinal rule is follow where the area is stable, right? So when you have a natural basin, a natural depression in the ocean, or other areas where you have sufficient water column isolation, to Steve's point, where you have these prop washes, vessel wakes, things like that, affecting the potential stability of the material that's placed there, is of primary concern. Along with that, the bottom sediment type is important as well. And that's because earlier in a question for Steve, we talked about what kind of material can you place here. So traditionally, if you have free product or sediments that are on the left-hand margin turning towards Superfund scale, not only should you provide the upper isolation, you also should provide the lateral and bottom isolation. So what does that mean? That means we need to assure that whatever is placed there, just like in a rock or landfill, is not going anywhere through the sides or the bottom, even though that process is slow and over some longer time spans. So that needs to be accounted for. And of course, the bottom sediment type and the placed material also plays into very closely with the dredged sediment properties. So this is a fill material, not the excavation that you do to create the CAD. And that's important because of that process of bearing capacity issue that Steve mentioned in Boston Harbor Cell that's been studied quite a bit, and it's fascinating to see that summary from Steve. So essentially the rule is make sure we know enough of the not only the in situ material, the material we're placing, as well how it is placed matters. And Bill hopefully will talk about this, because the density and the in situ void ratios are definitely a function of what material, how it's placed, whether it's through pipelines, whether it's through bottom split hull barges or buckets in some cases. And finally, the groundwater flow is an important process to consider as well. Other siting considerations include, where we put it, and I'll touch upon that during the case study. The shape, the length to width ratio, sometimes the orientation. Do you put it parallel, perpendicular to the channel? What kind of freeboard should we need here? And this is a fascinating topic because in my mind, if you're spending, CAD definitely is not on the cheaper end of spectrum, right? You have open ocean placement and you have level bottom capping. which would be more cost effective in the range of spectrum of things. Jake wanted me to touch upon cost, and they're very site specific, but I would say generally, if you look at a broad range, it's maybe $25 per cubic yard of capacity gained to about $50 to $60 per cubic yard in terms of, again, capacity gain. So that's the capacity of the CAD cell, not the excavation. And typically those costs include excavation, placement of that material offsite, sometimes back in the CAD, and also the dredge fill cost. And oftentimes the dredge fill cost is zero because it's coming from another dredging project and they bear the cost to transport. So all of that plays into this. The other factor related to the analysis we talked about earlier is the volume change. So when you disturb a dredge sediment from a channel, we're increasing the void ratio, we're bulking it, quote unquote, and typically you can gain anywhere from 25% to 40% increase in volume. Once you place it, if you have good dewatering controls like you would in a confined disposal facility, you can get good shrinkage, and sometimes you bring the material to less than one. So in other words, you get a shrinkage, quote unquote. In an aquatic setting where you don't have that ability to control the water that much, you would not get to below one, but you'll be somewhere in that 1 to a little over 1 ratio over time. And you could pre-consolidate this, but that means losing capacity. But the other fascinating factor is most of these CAD sites, once they are full or technically done with, they do sit lower than the nearby elevation, which I'm still puzzled a little bit, because if you think about maximizing the cost to the owner, you would think you can fill it all the way up, and we have science that supports it. But perhaps the idea is, people want some factor of safety, and therefore you follow the traditional freeboard kind of analysis that you would in an upland kind of setting. We can model the placement. This is the Adams suite of the Army Corps of Engineers ERDEC model, very true and tested. Of course, it's a function of what you put into the model. So we need to do settlement tests and geotechnical analysis, but you see the tools here from anywhere from the single dump fate. So again, in this picture, it simulates the split hull barge kind of placement. It can simulate other placements as well. Multiple dump, it simulates multiple placements, and long-term fate, happens. It looks at what is a long-term dispersion, settlement, things like that. So based on the specific application, we can use any one of these to simulate the placement. The other component of this is really what the sediments does once you follow the place, once you place the material. So number of processes here at work. Steve touched upon this. The reason that the cells may be sitting lower is maybe there's enough sedimentation here. These are quiet areas, hopefully. So that process will happen over time. This is existing sediments. We need to know what kind of transfer can happen between the placed sediment and the native sediments, especially if the material is contaminated. You also need to look at partitioning of contaminants, especially on the PAH, NAPL, PCB kind of range. There's other processes like diffusion and dispersion that are chemical gradient-driven processes. And obviously we have groundwater flow. So the groundwater can push it up or down or sideways in case of a cell that doesn't have a good lateral containment process, or a good material that would make it harder for the material to go sideways. So in other words, a lower permeability material. So technically, the more the contaminants, the lateral layers and the bottom layer should be low permeability compared to what you're placing within the cell. And then you have this cover material. Thickness is widely varying, sometimes a couple of feet, sometimes tens of feet. And again, depends on where that material is coming from, whether it's from another dredge project, in which case it's not a lost volume. And at the very surface, we also have processes like bioturbation, and then the whole host of physical forcing that we talked about earlier, which is, essentially all the other things, prop wash, hydrodynamic forcing, and things like that. So in the few remaining minutes, let's look at a few case studies. So here I have the Port Hueneme project. So it is a combination between the Port District, the Navy and the Army Corps of Engineers, this harbor needed to be dredged. There was significant amount of contamination. So they came up with a concept for a 10-acre CAD cell. They dug about 50 foot deep in 35-foot water depths, and they aimed for 500,000 cubic yards of capacity, of which they only used half of that, which again goes back to the earlier point of underusing these cells. But here are the contaminated material pockets. This is the area of interest. What they did over time was dug this material, and this happens all the time in CAD. So when we talk cost, oftentimes this cost is not credited towards CAD. So in this case, what they did was they dredged they excavated the CAD sediments, which happened to be good quality sands, which is pumped right into the beach. So the cost benefit of this beach nourishment should really be offset against the cost of CAD, which was not done and is not typically done. So that's a flag I would put there. But essentially they have a beneficial use. Most CADs look for good quality materials they can reuse in some way, shape, or form elsewhere, thereby technically lowering the total cost if you were to credit for that usage. But following the depression, the digging of the CAD cell, they came back, moved the contaminated materials, in this case with pH and PCBs, DDT, and some other contaminants. They placed it back at the bottom of the CAD cell. And then the final step was they came back and put the capping material or the clean material on top of this. So here's the filling process, the excavation process, the dredge working there, this filling process with the typical scow split hull, raining the material down, again as low density placement. You can see the schematic here, and significant amount of placement of contaminated sediments, following which the final concept is they would have this rip-wrapped armor, and why that was put in this case was because it's really the issue of I see Jake's hand there, so I have a couple more minutes, I'm guessing. So essentially, it's to prevent against that prop wash is really why this was done. Here's another example of Masonville dredged material facility. So this is again about a 5-acre CAD cell. And compared to this cell, which is a upland CDF or nearshore CDF, is about 100 acres. So you can see these are smaller cells compared to this, hence the challenge with cost. But essentially what was done here was they wanted to pilot test, can they build CADs in Maryland? And that was the objective here. So to do so, they did a comprehensive study, and in the GIS kind of setting, the first rule is find out where activities are in the harbor. So in this case, shipping channels, federal channels, access channels, anchoring areas. You want to DMCF, dredgement containment facilities. You want to stay away from all of that. And then you'd follow up with samples, geotechnical samples, to understand the type of material. Obviously, we're looking for environmentally non-sensitive areas, hydrodynamically quiet areas through modeling. And then we have geotechnical locations as well, so that we can get this good quality sand that we can reuse. And in this case, we ran a comprehensive 3-dimensional hydrodynamic model as well. That'll tell us, how this material and the CAD cell would be stable over time. And the last case study I have is Newport, and this I wanted to highlight because of this hybrid option. So they have a deep ocean placement, they have a nearshore placement off the surf zone, and then they also have placement, within the channel itself, which is a CAD kind of concept. So again, similar concept. The only difference here is that they have this interim cover. So if in cases where you're not fully using the CAD cell, you do come up with this interim cover if the material is unacceptable to be left alone. And then you can come back and fill for the second tier placement over time. This is the schematic of placement. I think, Steve covered this, so I'm not going to spend time there. So in my final slide, in terms of reflections on where are we with this based on national experience, I think the point is well established earlier. We need to study these very carefully probably for, first and foremost, for sediment strength and consolidation, because some of the CAD cells where people attributed it to failures was because it was really a bearing capacity failure, because people didn't account for enough time for consolidation of the placed material before the cap was placed afterwards. Water quality effects are critical, especially as the contamination is on the upper scales. Modeling of the cap effectiveness as well as the cell effectiveness are important as the material degree of contamination goes up. And there's this need for long-term data in terms of monitoring, maintenance, as well as guidance. There is no real guidance per se. There's a lot of Demos reports, which are great, but there isn't really a CDF kind of CAD cell design manual that the Corps has out there that people can use. So it's largely based on our experience to date. So with that, I will stop and turn it back to Jake.
Thanks, Ram. Thank you very much. Does anyone have any questions for Ram? I have one, but I'll let anyone else go first.
Yes.
Oh, go ahead, Steve.
Yeah, Ram. So I'm curious, in the sites that you've looked at, has groundwater advective flux through the cell, been a limiting factor anywhere? It typically just hasn't been so much of an issue in the New England harbors, but it seems like it really could be.
Yeah, the sites we looked at, it hasn't been, but it's certainly something we look at to see, whether it could be an issue. But you're right, it's traditionally not an issue. You want that to be kind of like an inward flow as opposed to the contaminants going outward. So, but it's mostly in that groundwater situation, the predominant concern is that upper layer and the transport up through that, especially as the material consolidates over time. So it's groundwater plus the pore water expulsion that happens due to consolidation.
Ram, I have one more quick question. You mentioned, and it seemed like you could say a lot more about the CAD cells sitting lower than adjacent grade. Is that immediately after the project, or is that due to consolidation over time?
Jake, I'm sorry, can you repeat that again? The cell consolidating over time, or what was the?
Yeah, so you mentioned that this one issue was CAD cells sitting lower than adjacent grades. And that was a concern for, it seemed like you could say a lot more to that.
Right.
But is that because primarily consolidation over time, or is that the CAD material sitting lower than adjacent grade immediately after the project is finished?
So it's actually both. So you do, account, and Steve mentioned this. So the consolidation could be depending on the material type. If it's coarser material, matter of weeks to oftentimes matter of months, sometimes as long as a year. So that definitely needs to be accounted for. The other one, what I was referring to was really whether it's dictated by the demand at the time, which could be the case, that they only need 250,000 yards, for example, but they build a CAD for 500,000 yards. So it may be a futuristic planning because you're dredging it anyway, so might as well dredge all the good quality sand. One thing I didn't mention, I'm glad you asked the question, is a Masonville CAD, they took all the good material. So you don't stop once you identify a source, through that geotechnical investigation, you find that you can dig, there's good quality sand that's, let's say, 20 feet in that area, and your CAD only needs 10. It's usually prudent to go 20 feet, get all the sand out. So use that sand for dikes or beach nourishment nearby. But that would mean you're leaving 10 foot of capacity in the interim. So I was just asking a question to this group as designers and operators to say, if you had the choice, would you consider pushing the envelope and filling it all the way, thereby getting the most return for the dollar? And the answer may be regulatory wise, we haven't done that quite so nationally. So, and it sounds like even in New England. So that may be the other issue. People, regulators may not be very comfortable if you say, I'm going to dredge 40 feet and fill 40 feet, with this material.
Ram, you mentioned a lot of the CAD cells you're constructing are in sand. What kind of side slopes are you looking at for those cells for construction?
So it typically varies. It's not necessarily always in sand. So it's really a wide range. So we typically look at geotechnical analysis and the type of material, and it could be a strata, as you go down, so sometimes we go through some layers to get to the sand. So there's no real one answer for that. So it really varies between sites.
Now we have up Bill Hansen, Senior Vice President of Market Development and Government Affairs from Great Lakes Dredge and Dock Company. And he's going to be drawing on his over 40 years of experience and giving us a dredger's perspective on CAD cells. You're up, Bill.
All right. Thanks, Michelle. Appreciate the opportunity to participate today. We've certainly learned a lot over the years we've been doing CAD cells. Just by way of background, Great Lakes Dredge and Dock is a 131-year-old now publicly traded company, 130 years based in the Chicago area, hence the name. Last year we moved the corporate headquarters to Houston. So we've got a lot of folks learning how to say howdy. The CAD cells, and Steve talked about this, some of the background of the first few projects, and this does go back to a great need nationwide for disposal area capacity. So this type of innovative thinking, innovative ideas, not just on the construction side, but really a big deal on the regulatory side to be able to take on this challenge and meet it with some unique solutions. I will say that we, as always, we encourage industry engagement, in dredging industry engagement in your discussions as you go through these projects and looking at unique techniques. Please don't get stuck on no. We find that a lot of times people will look at the existing fleet or the existing work types and think that that's all we do and that's all we're capable of. I think you'll find dredgers to be quite entrepreneurial and also quite innovative in the ability to, or interest in actually trying some different things and doing things differently. And certainly CAD cells are a big part of that, the underwater part. So if we can go to the next slide, please. And certainly, as you talked this morning, there's been a great project track record, and hopefully this will lead to doing even more of these in the future as an acceptable way to tackle that issue. I've got some challenges I'll talk about at the end, but it's even though a lot of it's been in the Northeast, we've seen projects Boston, New Bedford, Providence, Yorktown, but also in Masonville and the Baltimore area, and then even in Newark Bay. And Ram mentioned the project in Port Hueneme, also a very successful project. So hopefully we've got enough to learn from and collaborate on for future projects. Next slide. Typically, and I'll show some photos here from our Boston project that Steve mentioned earlier. It was an interesting project in a lot of ways because a lot of this is fairly new, and we were able to. And probably the biggest challenge on this one, initial challenge, was what to do with the surface materials. In that case, there was no place to temporarily store the surface materials as they were being dredged. So we actually had to dredge material and store it in our barges until such time as we were able to dig enough of the CAD cell to dispose of that material within the CAD cell. Typically, these projects are done with our large clamshells. Those projects, the buckets on those can range anywhere from 50 cubic yard, actually up to 70 cubic yard nowadays for the light material, the surface material, the mud, and all the way down to 12 to 14 cubic yard for the hard digging buckets. That's to remove the clay and then harder material underneath the surface material. The difference in the two is the Environmental buckets weigh about, for order of magnitude, 50 cubic yard bucket will weigh about 25 to 30,000 pounds, whereas a hard digging bucket, 12 to 14, can weigh up to 70,000 pounds. And that's just to help dig the harder material. Large scow capacity becomes a big cost driver at the beginning of the projects, and again, to have a place to store all the light material. Once you get into the harder, and then also that scow capacity becomes important for hauling the denser, cleaner material offshore. That's a big cost driver because the haul capacity. And it's interesting to note just how things go. Back when we did the Boston job in the 90s, a 4,000 cubic yard scow barge was considered large. We now regularly use 8,000 cubic yard scows capacity. So a big difference in size and capability there. Next slide, please. These projects impact a lot of stakeholders, and typically working in or around a navigation area. So we have to be very cognizant of the stakeholders involved. In our projects, it's typical that we're not allowed to impact navigation. So we work very closely with the ports and the local port users and the pilots to make sure that they understand what we're doing and we understand what they're doing. If we need to move out of the way for the project, and we can do so for a ship coming in, and then just move back on station. Next slide, please. Bathymetry, this is just a shot I threw in there to show how we laid out the Boston job. You can see at the lower half, the dredge cuts being laid out, typically about 100-foot wide cut, depending on the dredge. In this case, in Boston, we were able to use 2 big clamshell dredges. And so we had a lot of equipment on site being able to move the material. I will say from a dredger's perspective, once you get into the meat of the dredging, which is the harder materials below, it actually becomes quite a I'll say fun project, because you're not typically dredging to a draft. You're not digging to a channel dimension for a maintenance project. You're actually just digging deep. And of course, there is a lower limit, but that means the operator can drop his bucket and get a full heaping bucket and load it into scow. And you'll see a lot of smiling operators during these types of projects because they can dig away. So next slide, please. Some of the challenges, several of the previous speakers have already talked about soils. I'll repeat this because the top 2 items, if you're designing any dredging project, the 2 most critical things are soils investigations, soils characterizations, and hydrographic surveys. Everything we do, everything we do in the estimating process to try to understand the project we're bidding on has to do with soils and surveys. So you cannot have too much geotechnical information, and you can't have too many surveys. In this case, removing surface contaminated materials, whether it's to an elevation, predetermined elevation, or just to a harder bottom, that information is very important to divulge and be transparent with the contractor. CAD design depths, we've seen everything from 65 feet to 95 feet, and those can be a little bit of a challenge for some dredges that typically are designed to dig deep water shipping channels to 50 feet. But the dredges, we can adapt our digging methods as well as even our equipment to do whatever you need to do. In this case, I like to say in dredging, it's mostly about horsepower and steel. And so for the most part, if you guys can just tell us what it is you're trying to accomplish, we can give you an idea of what it'll take to do that. And we'll be glad to engage with you even before the bidding process. I'll repeat industry days, discussion with the dredging industry before these projects get get spec'd out is critical. We like to jab the Corps and then our other good clients that, it doesn't do any good that you guys take 10, 15, 20 years designing a project, and then you give us 30 days to take a look at it and bid it. It's not fair to us, not fair to you. So the more you can do to include the dredging industry in your early design and concepts, the better off you are. Slide slopes were discussed. One of the challenges we ran into in Boston, or one of the good success stories, is that the material actually stood up much steeper than designed. And so we were able to work with the Corps to realize that the big issue in CAD cell design, you're actually looking for volume. You don't really care what it looks like on the bottom, other than you obviously worrying about structures and some things like that. So if you're looking for volume, give us some flexibility to achieve that. I've already mentioned handling of surface material. The first project, we had to store a lot of material in barges, but subsequent projects haven't really had that issue because you've got CAD cell. You can actually transfer some of the CAD material, some of the contaminated material into the CAD cell without having to worry about the storage of material. Contract flexibility is absolutely key. A lot of these projects are new and innovative, and I think it's good for everybody to understand, from the contracting folks to the regulatory folks, that what we're trying here is keep the objective in mind. Again, if you're looking for space and volume in the cell, then let's make sure we get that, not have to suffer through trying to get every part of the bottom to depth and every side slope perfect, because that's really not the purpose of the project, and that'll lead to your project costs going up, and also this contractual friction that's not good for anybody. I will say that, and I was glad to hear Steve talk a lot about the follow-on monitoring of the projects. I served on the Corps of Coastal Engineering Research Board, and I know that there's a lot of monitoring, a lot of modeling that goes into these projects up front before we ever get involved. But we seem to see a lack of follow-on monitoring to support the modeling that was done up front. So we would encourage unlimited amount of after the fact monitoring of these projects, the success of them, just so you can tweak the future designs to make sure they're more efficient and actually function as designed. Next slide. Just a couple quick ideas on things we look at as we get into these projects. I mentioned the soils. This is fairly typical of things we look at as we bid these projects. We can do a lot of geophysical work. We can do a lot of physical soils testing, but all that's key to us analyzing the projects and reducing the risk and understanding what it is we're trying to do. Next slide, please. We will take all the data you give us, all the borings, all the geophysical, and we will lay it out in a fence diagram like this, where we try to work with you to understand, again, what material we're going to be dredging, what type of equipment's appropriate, and what challenges we're going to run into if we're expecting, for instance, mud and we run into sand, or vice versa. Those can all have impacts on the overall success of the project, not just from the construction point, but also from achieving the regulatory objectives. Next slide. And then finally, just another one of the 3D shots from Boston. The top darker area there is actually a cell that was dug to 90 feet. The one just below that, and I guess that could be magenta, is to the 65-foot range. And then on the right-hand side, you'll see the light blue. That is actually a capped cell. So a lot of good track records, a lot of good projects. And so I think they all deserve not just upfront discussions with industry, but also after action reports, after action studies to make sure that they perform as expected. And I think that's the last slide. Yeah, so glad to take any questions now or in the future panel discussion.
Thanks, Bill. Again, I'll invite anyone else to come up with questions for Bill. But can you speak a little bit about the flexibility, how flexibility played a role in in Boston, the Boston CAD Cell particular, and how Great Lakes dredging, and Steve and other regulatory folks were able to come up with a successful solution, even if it was different than in how initially envisioned?
Sure. And I'll say total transparency here, that a lot of times what we find in projects like this is that they get designed and the expectation contractually by the contracting officer is that you will provide, if it says 95 feet, you'll provide 95 feet. If you provide, if you want 1.5 to 1 slopes, you're going to dig 1.5 to 1 slopes. Well, all that, that's fine, we can do that, but all that costs money. And the fine tuning, if you will. The interesting part too, in the mid 90s, multi-beam was just starting to be used as a contractual tool. And it really had a big impact on the surveys and the acceptance of the projects. In fact, we joked at the time that using multi-beam, you can find a beer can at 50 feet. But what's the point? If you, what are you really trying to achieve here? Ultimately, for a CAD cell, again, you're looking for volume, you're looking for capacity. And so whether it looks like a nice, neat box, 95 foot deep, 1.5 to 1 side slopes, versus having 1-on-1 slopes and going a little bit deeper, the idea was to provide the capacity. And so we saw a lot of flexibility. That was an early on project. I had to hand it to Core and the folks involved in that project. They were very flexible. They were also made sure that the project objectives were achieved. And so we did learn a lot on that project from that.
Yeah, thanks, Bill. And then, Steve, you're coming back. Do you want to speak a little bit to that?
No, I actually had another question for Bill, just related to, I remember the evolution of using the hopper dredge for capping there. It originally was, pivoting based on its own bow thruster, and it got some coverage, but in the end, using the tug kind of teed up. And I'm curious if that's ever been used on a more traditional capping job, anywhere else around the country, because that in the end ended up being very successful for even placement of material.
Actually, no, Steve, it hasn't been used elsewhere. That was kind of a unique, and again, the flexibility that was allowed on that project, because a lot of times in these projects too, we see the requirements being dictated and actually become regulatory and legal. And we were actually allowed to do some things here, and you had some smart people on the project to say, yeah, let's try something and see if it works. If it doesn't work, it's okay, we'll try something else. And so that's really what made this work. And I know, Steve, you and I joked about this earlier, is that using the Cape Cod material as a value engineering proposal, we actually won a Vice Presidential Al Gore, I can't remember if it was a Silver Hammer or Golden Hammer Award, but it was a
Silver Hammer, yeah.
thing. Yeah. And but it was cool to see people with open ideas and willing to try things, that you weren't holding a regulatory or a contractual hammer over our heads.
Thanks, Bill and Steve. I have another question for you, Bill, but it'll wait for later.
Okay. Standing by.
Great. And final for our presentations is Johnson, who is a associate with Environmental Services US New England in Stantec. And he has a focus on freshwater and marine studies and evaluations. And he's going to be speaking today about the Portland Harbor CAD cell investigation and permitting, and his extensive history with that project. So we cannot wait to hear it.
Thank you, everyone, for this chance to present. I'm speaking to the Portland Harbor CAD Cell and Dredge project today. This project has been going on for about 5 years. The timing is very good for this presentation. We just received final Army Corps permits for the project and are going after federal funding now. So completing the investigation and permitting phase. I'm certainly speaking to the project today, but it was a team effort. Some consultants include Pierce Atwood and Campbell Environmental and Apex, as well as the engineers on our team who did a lot of the actual legwork. A lot of topics to cover. I'm going to kind of go through this relatively quickly, kind of hit the high points, some lessons learned, and I'm happy to go into more detail either during questions or the breakout session or the panel discussion. I'll start off mentioning it was very much a collaborative effort. I consider this sort of a public works project. We were working for both the Harbor Commission and the cities of Portland and South Portland, but very closely with all the regulatory agencies, EPA, Army Corps, Maine DEP, DMR, Submerged Lands Program, Historical Preservation Commission. This is a unique project, and especially being a dredge project that had wide community support from environmental groups, including the Friends of Casco Bay Estuary Partnership. The local lobstering and fishing industry was on board, as well as the groups like the Waterfront Alliance. And we have all our peers and waterfront and marina owners that the project will benefit. This slide gives us an overview of the project itself. We're located here in Portland, Maine. Portland's the largest city in Maine. This historic port that's operated for hundreds of years here, a couple hundred years now. So we are spread out. The red here we're seeing is the dredge areas that we're targeting as part of the project. And in blue on the shore of South Portland in a shallow subtidal flat is the proposed CAD Cell location. So these are our areas for context. There's marinas, which are primarily located on the South Portland shore here to the south, and then the historical working waterfront in Portland to the north. I should mention, it is really two separate projects, and it was two separate permits. They're very closely tied. The CAD Cell we permitted separately. But it was informed by all the dredge volumes from the piers and the wharves and the marinas. So closely tied together, two projects closely tied together. Getting into some of the background need here. Portland is a working waterfront, Portland Harbor, and there's a limit on non-marine industry along the waterfront. So many of these piers support fishing boats, fishing processors, and marine industries. Historically, there was a lot of manufacturing on the water, transport of coal and whatnot. So a lot of these sediments were laid down over the last 100 years, but because some of the factors we discussed earlier with the cost of both testing and the actual disposal, nothing has been done. So the harbor's been in a stalemate, and the cities and the Harbor Commission has certainly been working on this project for over 20 years. A lot of the work that led up to this prior to 2016, they came to the point where the CAD Cell was the preferred alternative. That's when Stantec got involved on looking at CAD Cell design and siting. There's a quick slide of analysis that the city of Portland did about some of the lost berthing on the Portland side. In red here, you could see berthing that's almost been totally lost through the sedimentation. Many of these areas now becoming intertidal. In the areas in yellow, there's certainly been a degradation in berthing where the full water depths are not realized. So there's been a shift to smaller vessels over time. So this is really driving the project, the need for dredging to support this berthing. As I mentioned, two projects. We had a lot of meetings with the agencies to kind of figure out how we're going to permit this early on. The permitting of the piers and the wharves and the marinas, there's only over 32 owners of a lot of different properties. So That permit, somewhat unique. It's going to be held by the Harbor Commission, but it's sort of an umbrella permit that includes all these different owners and properties. The CAD cell was permitted through the city of Portland and South Portland, so they will hold that permit for the CAD cell. And I should note that the dredging is, we have a proffered permit for that, and we expect probably a full permit this week. So the project will be fully permitted for both the dredging and the CAD within weeks. Touch on a quick lesson learned. I think Bill mentioned this, the interaction of projects with the federal channel. We certainly knew that we had to do consultation under Section 14 of the Rivers and Harbors Act, we call it 408 consultation, where a project will potentially impact the federal channel. But we didn't realize that the level of effort was a little more than anticipated. We have a few dredge areas on the outside of these piers that were in the federal channel setback. So that requires a review by the Corps of Navigation folks. And you can't get your full permit until you get permission, your 408 permission. So it held us up a little bit, and it applied to the CAD cell too. Although the CAD cell's outside of the channel setbacks, we need to do an entrance channel into the CAD, which I'll speak to in a minute, which did interact with the federal channel and required additional work on our end. Our project itself, I think, is very unique. It's not part of a federal navigation project, as others have spoke to. It's the private piers and wharves primarily, as well as those owned by the cities. And there's not federal funding for dredging for a project like this. So I'm not a brownfields expert, but Campbell Environmental led that. We did get a brownfields grant for design and permitting of the dredge areas for the piers and the testing. I'm told it's one of the first of its kind in the US to evaluate sediments for dredging in submerged lands. So the CAD cell funding was through the Maine Department of Transportation, as well as the City of Portland and South Portland, for the investigations of the CAD, siting, and the permitting. I'm going to start off talking about the dredging a little bit of the piers and the wharves. It's an example of some of our dredge areas. We started off doing a bathymetric survey of the harbor, so we had a good baseline. Went to all the different owners. Some owners have an entire pier, other ownership is broken up along a pier, so there's a lot of consultation with owners. Initially, taking the bathymetric data to them, talk to them, okay, what design depth are you looking for? What area would you like to dredge? And that resulted in designing all these polygons, estimating dredge volume, which ultimately informed the CAD cell design. So we're looking at 32 different owners, 47 individual properties, 21 piers, 10 marinas, Portland Public Boat Launch, and the Portland Commercial Barge Landing. And as I mentioned previously, some of these areas are literally intertidal now, so that was another slight hurdle in the permitting, where you're dredging in intertidal areas, you're converting to subtidal, so that's considered an additional impact that we had to work through for the permitters. And all of this material being disposed of into the harbor, Portland Harbor CAD cell. As part of the dredging of the piers and wharves, Maine DEP asked us to characterize the material for placement into the CAD. So we did vibra cores at the different dredge areas, testing for metals, pHs, pesticides, PCBs, to characterize that material going into the CAD. There's a little snapshot of some of the material looking at typical silty anoxic sediments, primarily in the harbor. Bit off topic, but I wanted to touch on this briefly because a lot of the folks who do dredging on the call run into eelgrass. This was actually a big piece of our project, a bigger piece than we expected. We had 2 dredge areas that had eelgrass impacts that totaled over an acre. One, the East End Barge Landing, which all the commercial barges and trucks and emergency vehicles go out to the islands from this point. So it's not all tide access now. They need to dredge an access channel in there. You can see where it's been scoured out from the barge landing there currently. We also had one of the marinas, which had an adjacent eelgrass bed, where eelgrass migrated into the access channel into the marina. Originally, based on the agency consultation, we had proposed paying into the inland fee program, which is relatively straightforward, not cheap, but it's straightforward. But little background, since that time, there's funds in the inland fee program for eelgrass restoration, but there's been no projects. So the EPA and NIMS came back and they said, we really like to see owner-sponsored mitigation. So we worked with the Harbor Commission and who regulates the moorings as well as being the permit applicant in the harbor. And then we had over 200 moorings that are traditional block and chain and eelgrass. So part of the mitigation project, we are going to be converting these moorings either to conservation moorings or moving them out of eelgrass beds, and we'll get credit for each mooring moved or converted. And then prior to the dredging of these eelgrass areas, we'll look at the balance of that, and if there's a balance, we'll pay into the inland fee program. So a lot of back and forth and agency consultation on eelgrass. Switching over to the CAD cell. We started the project in 2016, and there'd been some work, some sub-bottom profiling, and the city had determined that the site off Fisherman's Point here was a preferred location. It was where we were going to start our investigations. But when this came to light, there was a lot of pushback from environmental groups and the fishermen because of current use of this site. So we had to go back to the drawing board, sat down with all the stakeholders, environmental groups, the owners, the fishing community, and reevaluated, and ended up with this site here near the Coast Guard Station in South Portland. It's a shallow subtidal flat outside of the navigation channel, in with minimal fishing effort, if any. Some of the other sites we turned down as part of the process was the turning basin, which was located in the federal navigation channel. The Corps had concerns about future deepening of the navigation channel there, and we didn't want to see a CAD cell located in the channel. The Turner Island site, which had plenty of room, but was actually shallow intertidal, and would have required some impacts to wading bird waterfowl habitat as well as shellfish resources. Fisherman's Point, as I mentioned, had fishing concerns, as well as Halfway Rock, which is located outside of the harbor and in a different water quality classification. So we ended up here at the Coast Guard Station. I think you saw a version of this figure from Steve. We're planning on CAD cell construction over one year during the seasonal dredge window. We have tested the material at the CAD cell site, and the surface material is actually clean. They tested it okay to go offshore, and they're underlain by marine clay. I'll touch on this briefly now. We can talk about it a little bit later, but we, based on all the research that's been done, and we summarized in our permit application as well as providing documents to the regulators. We're proposing a natural cap. The CAD cell will be constructed below grade. It's located at the outlet of Mill Cove, which is a large intertidal flat, so it's a deposition area to begin with, and it's basically going to be acting as a sediment trap. So no sand cap and natural deposition over time. Here's a shot of the CAD cell design. 9.5 acres. It's 376,000 cubic yards of material being dredged out for a capacity of around 273 cubic yards of fill material. As I mentioned previously, there is an access channel into the CAD cell here. This was probably the most complex consultation piece with the Army Corps as part of the 408 process, because there will be an entrance berm following filling of the CAD cell that will be constructed across this to bring basically the entrance channel back up to grade. A little bit on the site investigations. We did sub-bottom profiling over the CAD cell location, as well as that one geotechnical boring. Very clear surface. It's a sandy silt going down to about 3 feet. This photo here kind of shows that break, and then we get into Sunscott Formation marine clay, which extends about 50 feet down. So shows up very clearly on, on the sub-bottom profile here, and this red is our boring location. This was all used for permitting design. The first step of the project, it will be a final design where we propose additional geotechnical borings and additional stability analysis to inform the site slopes of the CAD cell. Here's quick graphical representation of those sediment horizons that we saw during the geotechnical boring, getting down to bedrock at close to 100 feet. As part of the CAD cell investigations, we did both intertidal, subtidal characterizations, a lobster survey. This photos are taken at a -2 tide, so portions of the CAD cell site were exposed. It's all silty, sandy silt. There's a European oyster bed that has colonized the area, which is a non-native species. And the deeper portions of the CAD are just the silty bottom, primarily dominated by green crabs. I want to touch on the sediment sampling we did for the offshore disposal as part of the regional imputation manual of the rim testing. These are our vibrocore locations. We tested down through into the marine clay. Touch briefly on a lesson learned. This 3-metal testing has been applied in New Bedford as a quick way to determine your anthropogenically impacted sediments on the surface, copper, chromium, zinc, that are relatively cheap test. So you can do a boring down through or a vibrocore, take samples at regular intervals, and when these 3 metals start to drop off, you know you're into your native sediments. So it actually graphs out quite nice. There's some examples of that from New Bedford in their permitting documents. What we found out here is that actually our site, the surface sediments are relatively clean. And once you get into marine clay, the copper, chromium, zinc levels actually tick up a little bit, which was news to us, but looking at the literature, that is a feature of marine clays. The province of Quebec actually has separate sediment screening guidelines for their marine soils or marine sediments because of this feature. So lesson learned, if your 3-metal tests, it does not work all that well when you're in marine clay sediment. Big picture project schedule funding, where are we now? So we've received our permits. As I mentioned, this is not a federal navigation project. So where are we going to get all the money? There's the federal US DOT, which is now called the RAISE grant, which was the build grant last year and previously called the Tiger grant. We applied last year as part of the build process. We're unsuccessful, but we're going again for the RAISE grant this year. The project has a lot of momentum, a lot of support from all the congressional folks and at the city and state level. It's really a win-win project. It needs to get done. These sediments aren't going anywhere by themselves. So everyone's very hopeful. We're working on that application now, which is due in July. As I mentioned, following award of the grant, we'll look at final design and bid specifications in winter 2021-22. CAD cell construction the following winter, followed by harbor dredging after that. There will be tipping fees associated with that. The federal USDOT grant requires 20% match, which will be in part paid by tipping fees, which are looking to be around $12 to $15 per cubic yard. The Maine DOT is also matching those tipping fees as part of the process. A lot of information, run through relatively quickly, but more open for questions and on any aspects of this.
Thanks, Michael. Very interesting. So something that came up. Well, Steve, do you have a question, or anyone else have a question? I'll open it up.
Yeah, I had a quick one. Michael, do you have a ballpark idea of cost for, where to get to this point, and roughly just order of magnitude, and how much did the Brownfields grant cover?
The Brownfield, I believe, was around $300,000 grant. So all in total, we're, probably around the $600,000 level for all the investigations and permitting, which is probably on the low.
Does that include some of the birth investigations as well?
Yes, which was primarily just the bathymetry and the vibrochlore sampling.
Okay, great, thanks.
So as part of the grant, we'll be looking at, and this is a can of worms, but we'll be looking at stability analysis associated with all those structures to inform final design of those dredge prisms, which will not be cheap.
So I have a question for Michael that may lead us into the general panel discussion. So in our breakout room, there were concerns that it's hard for private and commercial dredging operations to get their hands on CAD cell, or like a CAD cell to dispose into. Is this a good model, this Portland model, where the town is leading an effort of so many different stakeholders? Is that a good model?
Yeah, I think it is. It's required a lot of dedication for 20 years by the Harbor Commission, by the city, to make it happen. It hasn't happened overnight for sure. And even just the investigations of permitting of the CAD cell were, always limited by funding to get to the next step. And so it would be nice to have more federal funds available for this type of work. It would ease the process for sure.
I have a question. Michael, I'm just curious, now that you have all the permits in hand, we've talked a lot about the design and the site considerations and kind of what goes into the cell. Now going forward, I'm kind of thinking back to one of the speaker's comments. Now going forward, what kind of permit conditions are you seeing to maintain and safeguard environmental quality and kind of monitor the cell and the water quality? Just kind of a overview of what kind of monitoring and reporting requirements that are associated with specifically with the CAD cell.
Yeah. As I mentioned, luckily we were able to build off a lot of the work by the Corps and others, and we provided a lot of that information as part of the permitting process. So I think regulators were well educated on CAD cells going into this, which was nice. We are required to do turbidity monitoring during both dredging operations. We'll have a third-party turbidity monitor out there and CAD cell filling. The Army Corps has requested pre-dredge meetings for both the dredge areas and the CAD cell to kind of kick the project off. They've asked for any final design draw changes. We like permitting for most projects. We permitted a worst case scenario as far as square foot of impact and the sizing of the CAD cell. So hopefully, based on any revisions, we'll be downsizing things for less impact, which will lessen the permitting hurdles moving forward.
Right. Any benthic habitat follow-up surveys or monitoring?
No, just long-term bathymetric surveys of the CAD, look at consolidation over time and stability of the side walls and entrance frame.
Okay, thanks.
So we heard Bill say earlier, Michael, that you cannot spend too much money on geotech and survey up front. And now we're hearing you say federal funds would go a long way in making this not just a step to get enough money to get to the next step, and federal funding was an issue for kind of the whole looking at the whole picture of the project. What was done in order to stage the design process or stage the data collection effort so that you get don't spend money up front, but you get to where you need to be when you're talking to Bill and other contractors at the end?
Yeah, so one borings, as Bill can speak to, is not a lot. But we realize, we know going in that once funding is received, we'll be doing additional analysis. Nice thing we had, sub-bottom's not that expensive to do. It can be problematic in areas with methane bubbles where you can't see down through the sediment, but that wasn't the case over most of the CAD cell. We had good correlation with our one boring and the sub-bottom profiling that gave us a lot of confidence that there was sufficient depth of sediments in that area for construction. So that was definitely a win. And up front, we know, the dredgers don't want to take on the liability necessary of not knowing what's there. They don't want to have any surprises, big boulders or ledge outcrops. So that's why we will put the extra effort to do the additional borings at the corners of the CAD.
Yeah, I think that's kind of the point. Good point, Michael, is that dredgers will take that risk, but I don't think you want us to.
Yeah.
The cost impact compared to the cost of additional geotechnical is quite a bit larger. So it's better to, if you can, to do whatever geotech you can.
Well, let's we can move into the general panel discussion with, thank you very much for the speakers and any questions. Michelle asked a question earlier that's good for all the speakers. Michelle, you want to ask it again?
Sure. I just realized that one thing we didn't really touch, we kind of framed it that a lot of times that the impacted sediment was kind of contaminated, but we didn't really touch on or speak to what kind of typical contaminants of concern that you see in your various roles with this kind of work. And I just wondered if somebody could touch a little bit on that. Not an exhaustive list or anything, because I know there are a lot of different scenarios and there are often multiple exceedances and things like that under state or federal regulations that one has to deal with for contaminated sediment. But I just wondered if some members of the panel could speak to what are the common triggers that gets an applicant looking at this kind of disposal option.
Yeah, I could just touch on briefly what we saw in Portland Harbor. Long history of industry, not super high levels, but we certainly have ERM exceedances, effect range, median exceedances of metals, pHs, some low levels of PCBs in certain areas that, as you would expect, the higher contaminant levels associated with those pier structures in the central portion of the working harbor. Less contaminated sediments on the South Portland side where the CAD cell was located. And as a side note, the Army Corps is not really interested necessarily in the sediment testing for what goes into the CAD. They're interested in what's coming out of the CAD for offshore disposal. So it was Maine DEP that was the driver of the testing for our CAD cell.
And I guess I could add, I mean, as you go up and down the New England coast, they're historic harbors. So they're all the old contaminants that you see associated with boat work, vessels, that kind of thing, the metals, copper, lead, zinc, that's sort of a background suite, as well as pHs, just the handling of all the fuels and things, as well as, there are a number of harbors that have old coal tar sites associated with them. So I would say those are sort of the baseline pulse that you're going to see, again, with some of the national standards like effects range medians, that you're going to see some exceedances. And then as you go harbor by harbor, be it PCBs like in New Bedford or pesticides, maybe somewhere down on the Cape, we sort of see, ones that rise above the other. Not so much some dioxins in Maine. I don't know, Ram, you probably have more on the West Coast where dioxin ends up being much more of an issue.
Yeah, I haven't seen much of that either. I've seen the usual PCB, pH, DDT, TBT sometimes, that's, and metals, of course. Yeah, but it's a typical suite of chemicals you guys mentioned.
I know we're going to lose Ram in a minute here, but I wanted to check. Did you have any sense, where would we have to push? It seems like this would be over the next decade, maybe some guidance related to CAD cells. And have you picked up on anything from ERDIC level, that's on the horizon potentially?
No, but that's the group I would probably push to get that sort of a guidance, or maybe given the activity in New England, maybe, it could be out of the DEMOS program, so, but I think ERDIC probably is the right avenue for the national kind of standard. The closest, like we discussed yesterday, Steve, I've seen is that a survey of CAD site paper by Craig Wort, former EPA, and Craig had done that for Environment Canada, but it was a pretty elementary kind of paper on where are the CAD sites and what are some of the global permitting considerations and other siting considerations. But we covered more in depth here than what's in that paper, but I'll send that around after this to the panelists, and maybe Jackson can circulate to the group.
And then in terms of some of the modeling tools, I don't know, Michael, have you done some preliminary modeling about, what might happen into the cells? I know some of the standard Atom suite kind of pushing the envelope in terms of numerically what they were set up for, this shallow water. I think it violates some of the underlying sort of principles, but that there certainly are more robust models available now just to give you a sense ahead of time as to, what might actually happen when you release that load of material.
No, we drew on the literature, model, both the modeling and observed results in our permit for that description. And we have the benefit of not depositing materials through a deep water column. Basically, we're in 10 feet of water over the CAD cell site. So there'll be some shielding from the actual CAD cell walls.
So I've seen three types of modeling, Steve. The first is the actual dispersion modeling, like the Atom suite, the one I showed in the slides, any one of those or combinations. The other one is the hydrodynamic modeling. So that is traditionally the wave model where you can superimpose ship effects on top of that. And then the third one, one of the schematics I showed is really a modified CAP model that we have extended based on the original work of Danny Reibel when he was at UT. And so we have basically taken that and added some components to it to make it more applicable to CAD cells. So that's the one we use for projects like the Newport CAD that I showed as an example. And then of course, depending on the consolidation, you can also apply the consolidation models to see how that would be. And that to me is probably the more tricky one, because I see a similar process like when you're trying to simulate consolidation in a typical CDF where you try to run a series of PSDDF kind of models. Here, the trick would be to match how the input is closely tracking the actual condition in the field. So like in a traditional CDF modeling, I would think you would want to modify it or track it and then modify it almost like barge by barge basis if the void ratios and other density and material types change in the field.
Kevin, I see you have you've shown your video. Does that imply you have a question? Or just want to show your face?
Nope, just turning it on.
Okay. Well, I guess Steve and maybe Ram have a question before you leave, Ram. That what we've seen here is that there's a big jump from upland disposal to open disposal, and this fills a much needed niche. Is there something, are there data gaps that are missing for how to, we heard from Michael that the permitting is a project unto itself. Are there data gaps that could alleviate some of that timing, or is it, what would need to happen to make this a little bit more quick of a process, I guess?
I guess I would defer to Steve on the timeline of the process. He's certainly more qualified than I am to answer that. I think the challenge would be, it's very site specific to the regulatory comfort level, as with any technology. And I think here the question would be, the long-term performance data. So if people are more concerned with, a certain community is more concerned with having a CAD where you try to consolidate sediments that are more on the contaminated scale, the question would be, is it protected in the long term? And what is long term? So traditionally in a contaminant world, in the Superfund context, we would want a minimum of 100 years of isolation. So I don't think CADs have been studied nearly in that level of detail to see, do you get that kind of protection? We do it on the cap where sites have to be capped, but I don't think we do it from a groundwater transport and impact to surrounding areas. But Steve, I'll defer to you on the timeline issue.
Yeah, for the timeline issue, I mean, I guess I would encourage sort of two tracks for if a given state area was interested in it. If you don't have an existing, DMMP, dredge material management plan that covers your entire area, the inventories, essentially, what needs to be dredged, either through your state's dredge team meeting, somehow get an inventory of that. And then, the two tracks would be, what does the Corps have on the horizon for federal dredging? Because that becomes an avenue that then you can cost share in terms of the potential construction of a cell should the Corps need to do that for the federal work. And then that's probably the most cost effective, because then you're just basically buying into a share of that work and letting the Corps do all of the essential behind the scenes sort of background work for it. But again, that typically can happen at a much longer time scale, because as we know, Corps work in a particular harbor is very much congressional funding dependent. The other is the model that Michael has relayed here, which is sort of totally independent of the Corps. And that would be a really good one. I would hope that a sort of a paper comes together after the fact that kind of shows the timeline and the various hurdles and steps along there, particularly given that you've demonstrated that there are some sort of levels of the avenues of funding that typically weren't thought of before, like the brownfields being able to pull into this. And I think that, even though it's been a painful 5 years, is probably a faster track than actually going to Corps, trying to wait and piggyback on something with the Corps.
And I will note that it was about 14 or 15 months following permit submittal to get permits in hand.
So I had one question for Michael. For the project you mentioned, it looked like there were a lot of structures right next to the dredge prism. So how are you guys taking on the liability for that, or will you require each individual dock owner to sign off a liability waiver?
Yeah, so that's a little bit outside of my wheelhouse. The city's dealing with that, but that's being worked out now. And we are including a line item in the grant for some of that stability analysis, and it gets complicated quickly on who's going to do it. Should we try to get grant funding for that, where they're outside the dredge prisms, but certainly associated with them. So it's going to be, yes, at some level, the pier owner is going to sign off. It'd be nice to have some stability analysis associated with that to refine the dredge prisms to the best of our abilities. If we don't have that, the dredger is going to look at setbacks for some of these structures, which may limit some of the material they can pull out. That's all being evaluated, and it's complex. Luckily, a little bit not something I don't have to deal with directly. So.
All right, folks, I have to excuse out of this now, but thank you for the invitation and the opportunity.
Good to see you, Ram.
Thank you so much.
Yeah, thank you, Ram.
Thank you, Ram.
And I guess I would have a question of our other state folks on here, to Brian in Connecticut there. What would be most helpful in terms of a takeaway that as you go into the planning part of this? You look like you're muted. There you go, Brian.
Yep, got it now. All right. Yeah, there's so many things come to mind. It's kind of hard to know where to start. I think, what I'm thinking about is, clearly you don't want to use the CAD cell option for just your sort of what I'll call run-of-the-mill sediments. Where a marina has material that, could potentially go to an open water site. But it seems like they want to reserve that capacity for the more challenging materials. And so I think we need to get a handle on what's the critical mass of that material that we need within the area of interest from the various entities that might require dredging, and what is the critical mass, and when would the dredging need to happen? Could the dredging be coordinated to happen within the time frame where you could leave a CAD cell open? So there's a lot of planning around just, I think, getting to leading up to understanding what the design needs to be, and then it's going to be a long timeline, relatively long timeline to get through the process of designing, permitting, constructing, and are all those entities still going to need dredging, or are they going to be past the point where they needed dredging and have gone to find other alternatives? I think there are a lot of things we need to grapple with there. I think certainly we are going to want to have a better handle on understanding water quality impacts and assessing how we meet the water quality standards when we do a project like that.
Because I think, from a state level, and it's probably similar to Portland, you would anticipate having a cell open for an extended period of time. Basically, because not everybody's going to dredge in a given year, and some of these are repetitive dredgers, and I, actually, to Michael, has there a timeline on that as to how long you anticipate this would actually be open?
Yeah, so there were some environmental fishing concerns about the length of time being open. We originally permitted 5 years, but there's actually, with the federal funding, it's by the time you construct the CAD, it leaves you about 3 years to get all the dredging done to utilize those funds. So it's expedited the dredge work. So now it's going to be over 3 years. And I will mention that, especially when you permit a CAD, you need to design it based on current need and justify that in your permit. But as we know, there's plenty of other sediments in these harbors that potentially could go in the CAD cell in the future. The Mass Port CAD cell in Boston Harbor that is now open. We've had 2 separate private projects that are either looking or have looked to put material into that CAD cell. So I know that was designed specifically for the navigation projects and then for Massport's needs, but boy, having that available for other private projects is important.
And Michael, you may have mentioned this during your presentation if I missed it, but is there a plan for ongoing monitoring during that period when the cell is open? Well column monitoring or otherwise?
After sediment disposal?
Yeah.
Yeah, it'd be the bathymetric surveys.
Okay.
Post construction. So no additional water quality monitoring, or at least required by the permit.
Okay.
But that's the kind of thing where it's sort of a new model where, I would ask around about potentially some of the semi-permeable membrane devices, particularly if you've got some organics in there, those are an ideal sort of let something sit for a month or two and you collect it back and sort of see what's the accumulation of contaminants there. Because again, I think we don't have a specific guidance on this. We don't have necessarily data. As I say, for Boston, there was a fair amount of work which was done at the time or during the consolidation phase, but then not really long-term chemical monitoring associated with it. But most of those are in sort of working harbors where, even the sediment, even though it's gotten better, it's still somewhat impacted sediment, which is ending up on top of them.
And as part of that final design, that's a plan to pull a long-term monitoring plan together for the city as part of that process.
But then, Brian, sort of on your end, what I could envision, particularly if you have the ability for the capacity and you make the cell larger, and you get sort of the worst of the material in that first, whatever you say, the first 50%, 75%, then you have the ability to say, gosh, this thing could stay open for quite a while, but we're taking material, the material which is by and large, because, you've got that sort of that headache or that complicating factor where it's both MPRSA and 404 potentially regulating some of these sites out there, and where some of the smaller projects, they're marginal, maybe somewhat elevated. They're not terrible. We think they would pass biological testing, but you don't want to ask a 2,000-yard job for a marina to spend $30,000 on biological testing. That becomes an ideal sort of avenue that says, gosh, this is contained. We know where it's going to be, and then not to have to require them to go the biological testing route.
Right. Yeah.
Keith, do you have a question? I see your hand is raised.
Yeah, I did. And one of the illustrations you showed what looked to me like interim capping. And I wasn't sure if that was something that could be utilized. In particular, I'm thinking strictly in terms of what we may need in New London and the Connecticut rivers. And so can anybody speak to interim capping other than what was just said about the semi-permeable membrane? Thanks.
Yeah, I'm trying to remember if that was in one of Rom's slides, but it definitely has been brought up before. But essentially, if you're going to have it open for an extended period of time and you don't want to have sort of the higher contamination material exposed at the surface, then you use some of your capacity by putting some material that has tested suitable, clean material, basically over the top of that. And so again, that's the trade-off of a few percent of the capacity. But now if it's going to sit for a whole season or two before you're going to place more material on it, you move forward. The other is, and I think this was actually done in New Bedford, where you are going to go from one dredge season to the next. Now you want to again sort of isolate the underlying layer, and maybe you do that with an activated charcoal addition to it. You put some coarser grained material in, which is actually going to work to compress this and expel some of the water, but you add some activated carbon to it to basically bind the contaminants up, and so I could see potentially a very large regional cell, which was going to basically have a 10-year horizon, have maybe several layers of successive isolation layers placed in the center of it, if it was going to go dormant for a season or maybe multiple seasons. And everyone's always happy to do that because it typically means a local dredging project, which doesn't have to haul to an offshore site, doesn't necessarily have to go through biological testing, the more expensive testing, you can just put it locally.
That's a great answer. Thank you.
Yeah, thanks. That speaks to the kind of the futuristic planning that I think Ram was bringing up, in that, a regional CAD cell like that seems like it would be hugely helpful.
I have another question. Has liability been a consideration in any of the CAD cell work to date? So, you know, you're taking contaminated material and concentrating it in a single location. Has concern with you know, potential ramifications of that in the future and liability associated with that been an issue at all?
That's a good question that I will take back to some of my core folks and ask them. What I mostly recall in the original Boston Harbor was the concerns related to, well, gosh, what if we want to deepen this someday? But not necessarily, you know, what if, you know, if something happens. I think because for both Boston and Providence, the cells are placed in the Federal Navigation Channel. The Corps, by default, they basically took ownership of them. But I will go back and see if I can follow up on that and see if there was a sort of an express piece. For Portland, it's a whole different scenario, and I'm curious, Michael, if that's come up at all.
Not that I could speak to specifically. It has come up in some of the city's discussions. We do have a submerged lands lease for the CAD cell because it is state lands, but long-term liability hasn't been discussed that I know of in depth on my level.
I mean, following up on that, one piece that I had mentioned to Bill before, at some point in time, you know, one of the Boston Harbor, the Mystic River cells, where Great Lakes was going very deep, they hit some hard material, they just kind of went around it and left basically, you know, some irregular bottom that basically got the capacity. But there wasn't sort of a memory of that at the Corps' end. And then I want to say maybe 10 years later, somebody did some bathymetry over the harbor. It was the Corps doing some standard bathymetry, and suddenly the bottom of the cell began to look like Death Valley or something. And there was all this concern that somehow the cell had ruptured, you know, the cap had lost its integrity, and required the Corps went out, DEMO's program went out and did some monitoring. And in the end, what it came back to was long-term settling. This was just beginning to follow the bottom topography, you know, that was 50, 60 feet below the surface of the cell, but over time it begins to mirror that topography. And so again, in that case, the Corps was taking the responsibility because those are in the federal channel. But this will be a good one to follow up on. I'll see if I can get an answer on that.
Well, I hate to cut this discussion short while we're all together, but I am going to turn it over to Jackson.
Thank you. So I just want to say thank you to Jake and to Michelle for putting together a great lineup today. I think it was great to see the speakers really play off each other. I think you guys could have went a long time had we not cut it off with some great back and forth. But we did get to cover a lot of topics, and we appreciate Jake and Michelle and all of our speakers today, as well as you for attending today's webinar. So there was a feedback survey link in the chat. Let us know how we did, good or bad, always welcome. Constructive criticism, just want to improve. The recording and the presentation will be shared with attendees in about 5 business days afterwards. So it'll be sent to you in a direct follow-up link, so you won't have to go searching for it. And then consider joining and getting involved. You know, CAD Cells is just one of the many topics this committee talks about, as well as all of the other committees and state chapters that EBC has. So again, thank you all.